Okay, so we're back. We're on episode 7D, the fourth calculation situation that you might come across when you're doing weak acid calculations. Kind of those interesting, kind of weird, unusual ones that you may or may not come across. But just in case you do, give you a little bit of a sense of how you might deal with those situations. So this little video's interesting little situation is, what do you do when the assumption doesn't work? Now that assumes that you're using the assumption during the calculation of the hydronium concentration for a weak acid. That makes, I'm making another assumption that you are using that technique to solve for the hydronium concentration in your algebra. If you're not using the assumption, then this is a waste of your time. Don't bother watching this, because this isn't, unless you're going to end up teaching the course and you might want to know how to do it for future reference. If you're using the quadratic formula, then you don't need to watch any further. Just go on to the next one. But if you're using the assumption, and then what do you do when it doesn't actually work? Okay, so I've got again, just as I've done before, I've got an example up here on the board. I'll walk through it. We'll get to how do you know the assumption isn't working, and then once you've kind of determined that the assumption isn't working, how do you come up with a resolution to that situation? Okay, so for those of you who use the quadratic and you're moving on, the next one is going to be, how do you tell, based on some of the data given to you, how do you tell whether or not you have a strong acid solution or a weak acid solution just based on measured values? Okay, so I'll give you kind of the quick and easy on that one. That one won't take very long. It's almost like solving a multiple choice question. Okay, so this one, the question that I'm going to give you is a typical weak acid question, pretty straightforward, kind of a generic one. So what is over here over my shoulder, what is the pH of a 0.500 molar HNO2 solution? So be really careful as I use this one specifically, HNO2, which is nitrous acid. That is a weak acid. One that's very similar to it, its cousin, as it were, nitric, which is HNO3, is a strong acid. So you got to look really carefully when you've got HNO anything. If it's a 2, it's a weak acid. If it's HNO3, it's strong, and then it dissociates 100%, or ionizes 100%. And when it ionizes 100%, the hydronium just equals the acid concentration. So HNO3 is a different story. HNO2, though, it's a weak acid. So we're going to follow the exact same plan of attack for weak acids. So number one, write down an equilibrium equation for HNO2 acting as an acid in water. 2, write an IRE and fill in what you know. 3, write the K expression. 4, fill in the values from the E line into the K expression and then solve for the variable. Okay, and then at the end, your X value is going to be the hydronium concentration, and then you answer whatever is being asked of you. So here's the question. So let's go through those different steps. So HNO2, forms a molecular solution. So I write aqueous in water, forms an equilibrium producing hydronium. And the anion nitrate. Okay, so that's the equilibrium. Then I write down an IRE table, ICE table, as it were. So IRE as per usual, water is a liquid. It doesn't change concentration. If you've been watching all of these series, that is probably getting fairly monotonous and kind of irritating. I know my students get irritated. I say it several times, so it never leaves their brain. Doesn't change concentration. isn't part of the K expression, isn't part of the calculation for an equilibrium constant, therefore you cross it out. Initial concentration of HNO2, 0.500, 0 there and 0 there. If you're just jumping in now and you haven't seen the previous one, the previous episode was about that hydronium in distilled water before you add the acid in. It's not technically 0, it's 1 times 10 to the negative 7, and when you've got a really dilute, really weak acid, sometimes that is a little bit more significant than just being 0. In this case, it's not going to be. So we put zeros in there. Then this is going to go down a certain amount. That will go up, and that will go up. So I'm kind of going through that fairly quickly because this has been a while back, and you've also done the equilibrium unit. So that concept of stoichiometry and the variable on that R or C line follows the stoichiometry. So I'm using X for every single one, and it's a 1-to-1-to-1 relationship. So they're all changing by an amount of X, whatever that's going to be. So I fill in my E line. And my IRE is done. The next step was to write the K expression. Hydronium, which is one of the products, times nitrite, which is the other product, over the nitrous acid concentration. Of course, these are all equilibrium concentrations. So I plug in what I've got on the E line. Oh, I got to look up the Ka value too, because of course I don't know it off the top of my head. So nitrous acid, HNO2 is 4.6 times 10 to the negative 4. Equals, and I've got X times X, that's X and that's X, according to the IRE table, over 0.500 minus X. Okay, so I've plugged in all my values from the E line. Now what I'm going to do is I'm going to do the math. But remember, this is the stage where you decide your pathway. You're going to go quadratic formula, or you're going to go do the assumption. And this is about the assumption. If you do the quadratic, you're not even watching anymore. So the assumption you write down, and you are assuming that that X you're subtracting from 0.500 is going to be significantly smaller than 0.500, therefore it makes no difference, and you might as well just be dividing by the 0.500. So you're assuming that the X will be significantly smaller than, that's why I do kind of the double less than arrow, 0.500. And so when we make that assumption, we obviously don't drop all the x's because then you wouldn't have anything to solve for. You drop the minus x part in the denominator of that fraction. So then what I've got is I now have simple math. So at this point I'm just going to, because you're kind of allowed to, you're allowed to we assume you know how to do algebra. So at this point you could just write x equals and just do the math. So I'm going to x equals, and then I will do the math. So I grab my calculator, and I'm doing 4.6 times 10 to the negative 4 times 0.5 equals, and then I'm square rooting. So square root to get the x, obviously. So square root of my answer equals, and x equals 0.015, and I get 2 sig figs because of that, the Ka having only 2 sig figs. It's 4.6. So I look at that value right there, and at this point, I mean, if you're not really paying attention, You're just kind of doing what you always do. You get x equals 0.015 and you move on, right? Because now you've got x, that's your hydronium. Negative log that, you get the pH. Done. However, if you are kind of paying attention, you're looking at that right there, and you should be asking yourself, is that okay? Like, is my assumption right? Did I actually make that a correct assumption? Now, how do you know if you've made a correct assumption or not? And this is kind of the critical part. Now, you're watching this part, and the title of this one is What Happens When Your Assumption Doesn't Work? So this doesn't work. So why doesn't it work? The assumption is, and it goes back to what is the assumption all about? What's the basis of the assumption? The assumption is that whatever x comes out to, it is going to be so small, it will be insignificant compared to the value you're subtracting it from. So you're subtracting it from 0.500. The assumption was that whatever our answer is, it was going to be so small that when you use your sig fig rules, it wasn't going to change. It would come out to 0.500 even if you did the subtraction and then applied the subtraction rules. So to check to see if it actually works or not, you actually just kind of, I mean, you can scribble it over on the side. I'll do it right above here. I'll just kind of put it in the middle of nowhere. If I'm checking it, what I'm doing is I'm taking the 0.500 and I'm subtracting what my answer was. 0.015. And you can already kind of tell that when you do that subtraction, whether you can do it in your head or you pull your calculator to do it, doesn't really matter. It comes out to 0.485. And because it goes to 3 place values, you need to keep all 3 of those place values. So the actual x value of 0.015, it actually did change what was in the bottom of the fraction. So it didn't come back and round back to a 0.500. It's actually been changed to 0.485, which means your assumption doesn't work. Right? The assumption does not work. So now what do you do? Right? Like, you've made this assumption, and your math, all of your math is based on that concept of your assumption being correct. So now, where do you go from there? Well, you've got 2 choices. One, you can kind of cut bait and go back and do the quadratic formula. Okay, so you can just say, the assumption didn't work. Okay, I guess I got to go back to this stage right here before I drop the x. And I have to multiply it all out. I have to move all the terms onto one side, equate it to 0, use my quadratic formula, figure out what a, b, and c are, plug them into the appropriate spot, solve. Punch it in your calculator and come up with it. That may be easier, especially if you've got the quadratic formula kind of pre-programmed into your calculator. That one works pretty quickly if you found that the assumption doesn't work. Or, so you've got that option, or you can, there's kind of a technique that actually takes into account, it's almost like a calculus concept, where if you continuously plug your answers back in, like if you solve and get an x value, and then you plug it back in here, and then you do it again, you get your new answer, plug it back in, get your new answer, plug it back in, get your new answer, plug it back in. What eventually happens is this, that you will eventually arrive, you will be moving towards, you're never going to arrive at it, you're going to be moving towards the actual answer. So when you do it once, you're getting closer to the real answer. When you do it twice, you're getting closer. When you do it 3 times, you're getting even closer. And every single time that you get it, you're getting closer to the actual answer. Well, what happens is, in chemistry anyways, that usually it only takes 1 or 2 times to plug your answer back in and recalculate it before you actually get 2 answers that are the same. And when you get 2 answers that are the same after rounding, then you know that you're approaching the correct answer, which is kind of it's a weird concept. It works mathematically. I'm not going into, I mean, ask your math teacher why it all works. But for our purposes, this is what it looks like. So the critical thing is to take this part of your equation, and every time you get an x value, like you get an answer to x, you plug it back in and recalculate. And in my class, I just call it recalculating. And I literally get my students to write recalculation, like recalc. And so the recalc would look like this. You take your previous answer, this 0.015, and you plug it back in. So I would have 4.6 times 10 to the negative 4 equals x squared over 0.500 minus 0.015. It's almost like I'm adjusting the bottom of the fraction because it wasn't quite right the first time, so I'm adjusting it to redo it. Okay, so I recalculate it. Now, I'm going to do this to many more sig figs than I'm actually allowed. So this answer right here, I'm going to leave it up here as 0.015. But this one down here, I'm going to write 165. I'm just going to add the 165 part onto that. Okay? Now what I'm going to do is I'm going to take my recalculation over here and I'm going to recalculate x. So what I'm going to do is I'm going to take 4.6 times 10 to the negative 4, right, the left side of the equation, times 0.485. So this times that down there, which is 0.485. And it comes out to a number. Then I'm going to take the square root. And it comes out to 0.014936. Close enough. Now, is it exactly what the previous one was? No, this one was 15165. This one is 14936. They're not exactly the same, but when we take sig figs into account, this one was 0.15. This one is 0.15. So no, they weren't the same, but when you round them, they essentially are. So this has to be your answer. Now, if I continue doing this, like if I took, instead of using 0.015 every time, I used a more precise answer, like 15165. And then the next time, I took this and plugged it in. What would happen is you would be getting, so here's the 0.15165 and here's the 0.0149. The next one would be a little bit lower, and a little bit lower. And you would be narrowing the gap as you did successive calculations. You'd be narrowing the gap, narrowing your gap, and it's kind of like almost like you're approaching a limit in math class. So if you're approaching a limit, that value that you will eventually get to, like if you did this out to infinity, you would arrive at what the actual answer would have been if you had done the quadratic formula. Okay, so if you know how to do this process, sometimes it's really fast and easy, and it only takes you one recalculation, as I've done here. It took one recalculation to get two answers that are the same. And once you get two that are rounding to the same thing, you stop, and that's your answer. Okay, so you had two choices when the assumption didn't work. Take the quadratic or recalculate by plugging your answers back in and kind of doing successive until you get two in a row. Now this, I didn't answer the actual question. So now I've got 0.015 as my molarity, right? So that is now the hydronium. That is your answer. Okay, I did one recalculation, I'm done. So now the pH is the negative log of the hydronium, which is the negative log of 0.015 which log 0.015 is 1.82. So how many sig figs do I get? So the concentration is 0.015. That's still old school sig fig rules from Chem 11. So that is 2 sig figs. So on the pH, numbers before the decimal don't count. Digits after the decimal do count. So in 1.82, the 1 doesn't count. I get the 8, I get the 2. pH is 1.82. So that successive recalculations is how you deal with an assumption that doesn't work. It takes some practice sometimes. You may never come across them, right? You might have a teacher who doesn't bother. They might even say don't bother doing it if your assumption doesn't actually work. Whatever, you're probably going to come to an answer pretty close to it. Or they'll just say if your assumption doesn't work, you must do the quadratic. In which case you'll have to pull your math skills out and use it. Okay, but there you go. If you are allowed to use that recalculation technique to come to the answer, there you go. Okay, so I will see you on the next one, and we'll be telling the difference between strong acid solutions and weak acid solutions just based on measured values. Okay, thank you. We'll see you later.